Alright, in this video we want to focus on numerical methods. Now, the numerical methods are used to find roots of single variable equations. Examples of numerical methods that we are going to focus on are bisection methods, Newton-Raphson method, regular false method, and others. So in this tutorial, our main focus is on bisection method. To understand bisection method, let's look at some example questions. Question A. Explain the concept of bisection method. How can you explain the concept of bisection method? Now suppose a continuous function f of x defined on an interval, closed interval ab, is given with f of a and f of b of opposite signs. Now the opposite sign here means if f of a is negative, then f of b is positive. And if f of b is negative, then f of a is positive. By the intermediate value theorem, there exists a point C which is an element of the interval a, b, such that f of c is equals to 0. If we take c to be equivalent to a plus b divided by 2, then there are three possibilities. That is, if f of a times f of c is less than 0, then the root exists between interval a, c. And that root, which is denoted as k, is equivalent to a plus c divided by 2. And if f of a times f of c is greater than 0, then the root exists between c and b, where the root is denoted by k is equals to c plus b divided by 2. But if it happens that f of a times f of c is equals to 0, then this means that c is the exact root. Now, part B. You're being told, use Newton's bisection method to determine the positive roots of the quadratic equation. Correct to three significant figures. The quadratic equation is 5x squared plus 11x minus 17 is equals to 0. Let's first determine the interval where the root lies. Now, to get the interval, we know that at the point or at the location of a root, there is a change of sign, either from positive to negative or negative to positive. Let's have a table with the value of x, and then let's get values of f of x. Using the given equation, 5x squared plus 11x minus 17, now when x is 0, f of x is negative 17. When x is 1, f of x is negative 1. When x is 2, f of x is positive 25. When x is 3, f of x is positive 61. So this implies that there is only a change in sign between 1 and 2, where sign changes from negative to positive. Hence, the root exists between the interval 1, 2. Having found that the first root exists between interval 1 and 2, we can now carry out the iterations. So x1 will be equivalent to 1 plus 2 divided by 2, which gives us 1.5. So this 1.5 is the value of x1. So what is the f of x1? Now that is f of 1.5. If you plug this into your calculator, you will get 10.75, and 10.75 is positive. So we picked 1, which is this, 2 here, then 1.5 is in the middle, in between 1 and 2. It is here. So 1 is negative, f of 1.5 is positive, f of 2 is positive. So meaning the root now lies between 1 and 1.5. So for x2, we pick 1 plus 1.5 divided by 2, which gives us 1.25. Now f of 1.25 will be equivalent to 4.5625. This implies that the root now exists between 1 and 1.25. Now for x3, it will be 1 plus 1.25 divided by 2, which gives us 1.125. Now f of 1.125 is positive 1.703. And that implies that the root exists between 1 and 1.125. Now x4 will be 1 plus 1.125 divided by 2, which gives us 1.0625. f of 1.0625 is 0.332031. So that implies that the root exists between 1 and 1.0625. For x5, we pick 1 plus 1.0625 divided by 2, which this gives us 1.03125. So f of 1.03125 is equal to negative 0.3388. Remember, f of 1 was negative, f of 1.03125 is negative, so meaning the root lies between 1.03125 and 1.0625. So for x6, we pick 1.03125 plus 1.0625 divided by 2, which gives us 1.046875. f of x6 gives us negative. So meaning the root still exists between f6 and 1.0625. For x7, we pick the value of x6 plus 1.1625 divided by 2, which gives us 1.054685. f of x7 is positive. So this implies that now the root shift again to 1.046875 and 1.054685. x8 will be 1.046785 plus 1.054685 divided by 2, which is 1.0507812. f of x8 is positive. So since it is positive, the root now lies between this value and this. Now x9 will pick 1.06875 plus 1.05078125 divided by 2, which gives us 1.0488 something. Now f of x9 gives us positive, so the root lies between 1.0468 and 1.0488. When we come to x10, the root exists between this and this, so we add them and then we divide by 2, which gives us 1.047815. So if you are keen, you will find that from x8 to x10 there is a repetition of 1.04, 1.04, and we were told to give our answer into 3 significant figures. Now if you are keen, you can realize that there is a repetition between 1.04. So this implies that into 3 significant figures, the root is 1.04.